Hello. By this time, you all know my name already. Just for the record, I'm saying one more time, I'm Dr. Memari. I'm going to perform experiment 5 of the lab manual for 1045 at Central Campus. This is specifically for Central Campus to help you to collect the data for the time that you cannot be in the lab and it's remote teaching. So I'm going to perform this experiment for you. And you are going to, based on the data you're collecting and your observation in this video, you would complete your lab report or data sheet for experiment 5 and turn in as the assignment to the assignment folder or to your professor. We are going to compare ionic compounds and covalently bonded compound. One of the behavior of the ionic compound and covalently bonded compound, or the difference between them, is conductivity. So if the compound, a compound to be or substance to be conductor of electricity, first of all, it must be ionic, and second, the ions must be mobile. So if you have an ionic compound that is in the solid form, it's not going to conduct electricity unless it's like a metal. We're not talking about pure metals. We're talking about compounds. So if it's ionic compound, it contains ions, and those ions must be mobile. There are three. Then it's electrolyte. If it's a molecular compound, then it's non-electrolyte because it does not have any ions. If it's ionic compound but it's solid, the ions are not mobile, it's going to be non-electrolyte because they are not able to move around. When it comes to electrolyte, we have 3 categories: a strong electrolyte and weak electrolyte and non-electrolyte. So what classifies as a strong electrolyte? Strong electrolyte, if you have a strong acid, would be strong electrolyte. If you have a strong base, is going to be strong electrolyte. If you have soluble ionic compound, so we know it's ionic and it's completely dissolves in water, then it's going to be a strong electrolyte. Weak electrolytes, those are the weak of each. So weak acids, weak base, and moderately soluble or slightly soluble ionic compound is going to be weak electrolyte. So we have 3 classes of weak electrolytes. The electrolytes that is going to be strong or weak based on the experiments we are doing today is going to light up this light bulb from the conductometer. We have a very simple setup for the conductometer that is very simple setup of conductometer. The conductometer is simple design of it is a light bulb that when you connect the conductometer to the power, the power comes in and it separates to 2 poles. Okay, so in order for the light bulb to light up, we have to see this. We have to see this light bulb lighting up. Electrons must go from one pole to the other pole. Air is not a good conductor of electricity. Air actually is a good insulator, so it's not going to move the electrons from one to the other. So if I plug this conductometer into the power of wall power now, you see the light bulb is not turning on, even though electrons are in one pole, but since they are not connecting or they are not transforming or transporting into the other pole, it's not lighting up. If we have a media here that is electrolyte, it will move the electrons and the light bulb is going to light up. So I'm going to follow the other thing that you need to know in order to record your observation. If the light is a bright light, then the compound is classified as a strong electrolyte. If it's a dim light or weak light, it's going to be called as weak electrolyte. If it doesn't turn on at all, it's non-electrolyte. That's based on the experiment. Now, if we have the first one, I'm going to follow the table that you have for your data sheet. For me, is page 61 now. Using that table, first item is this distilled water. So I'm going to place the conductor holes inside the liquid and connect. Okay, light bulb did not turn on. Water is a molecular compound, so it is expected not to have any conductivity. So it's not a conductor of the electricity. Next is going to be, I have the tap water here. For the tap water that I have here, I'm going to just use this tap water here, trying to see if it's going to conduct electricity or not. Okay, it does conduct electricity. I don't know if you could see or not. Okay, I'm going to unplug and plug back in. But it's very dim light. That very dim light, meaning that it's very weak electrolyte, because it's a tap water. It could have some salt in it, from like some salt that is in from the chlorine or other contaminants that is in the tap water. So tap water is conductor of the electricity, but distilled water is not. Like seawater is conductor of electricity because it has lots of ions, lots of salt in there. The more salt in there, more conductor. Methanol is the next one. Methanol is a organic compound, is a molecular compound, and because it's molecular compound is not expected, but that's not what we are here for. We are here to experiment. Actually, by experiment, we are trying to find out if it's going to be conductor or not. So the next item is methanol. The light bulb did not turn on, not even a dim light. We call that non-electrolyte for methanol. So methanol, non-electrolyte. Next is aqueous methanol. That means methanol mixed with water. So if I mix water with methanol, if methanol had dissociating hydrogen, basically was like an acid. The hydrogen would separate, generate ions, and then you would see the light. But methanol does not dissociate to ions in water. Some compounds, they dissociate to water, to ions in water. When you add water, they dissociate. So like acids, they dissociate in water. But if you don't add water to the acid, it doesn't dissociate, so it doesn't generate ion. So I'm going to repeat one more time. Acids, like glacial acid, when it's glacial acid, that means it's concentrated 100% acid that is going to the pure acid I have in the beaker now. I need to wash my hands before anything. Okay. Lesson learned. Okay, with the glacial acetic acid, we are going to see if it's going to conduct electricity or not. So glacial acetic acid, that means pure acetic acid with no water, no ions. So acid do not act as acid unless they are inside the water. So glacial acetic acid, that would be non-electrolyte. Now aqueous acetic acid means that I have that acetic acid. I'm going to add some DI water, going to give enough room for DI water to the acid. When we add water to acid, the acid is going to release hydrogen and the acetate ion, so is expected to have a dimmed light. So you see that dimmed light is created there. So you have that dimmed light. That means weak electrolyte. And why is weak electrolyte? Because acetic acid is a weak acid. Because it's a weak acid, it's going to be weak electrolyte. Even then, it has to be, basically, it has to be in water in order to show those ions. After the aqueous, then we have sucrose. What to expect from sucrose? Is sucrose electrolyte or non-electrolyte? First of all, it's solid. Even if it was ionic, it would be non-electrolyte because it's solid compound. But beside that, sucrose is molecular compound. And since the sucrose is molecular compound, being non-electrolyte, I'm not surprised it is non-electrolyte because it is a molecular compound. It does not have any ions. Next, it would be sodium chloride. Sodium chloride, but solid sodium chloride. Your solid sodium chloride is going to, let's see what we have for solid sodium chloride. When we connect it, no light, non-electrolyte, because there is no light in there, so it's going to be non-electrolyte because it's solid. Now, if we have NaCl in water, so basically we take the NaCl, place in beaker, and we add some DI water. So this is the proof that if your ions exist, the ions are there, but they are not mobile, it's not going to be electrolyte. So your ions must actually be mobile. They should move around. So for sodium chloride, in the aqueous solution of sodium chloride, it gives bright light. That means this is ionic compound that is completely soluble in water. So it generates lots of light ions that transfer the electrons or the electricity, conducts electricity, and we get to see that. Okay. Light. So a strong electrolyte for sodium chloride solution. Solid sodium chloride with non-electrolyte. Next one on the list is mercury 2 chloride. Mercury 2 chloride. All chlorides are soluble except for mercury, and mercury silver and lead. So mercury 2 chloride, it doesn't generate ions, even if it's added to the water. Because it doesn't generate ions, it's going to be non-electrolyte. This was the mercury 2 chloride. So not electrolyte. Next, HCl. HCl. We organize HCl. What do you expect from HCl? You think it's going to be electrolyte or not? What's the question you have to ask yourself? HCl is hydrochloric acid. Is it a strong acid or weak acid? And if you know HCl is a strong acid, then you can answer the question even before testing. Strong acids are strong electrolyte. and strong electrolyte gives bright light. So HCl is a strong electrolyte. Strong electrolyte gives a strong and bright light. Next, we have NaOH. For NaOH, sodium hydroxide is also a strong electrolyte because sodium hydroxide is a strong base. So if you have sodium hydroxide as a strong base, it's going to give us bright light, which means strong electrolyte. So we are done with that table with list of the substances we want to know if they are electrolyte or not. We are going to complete the data sheet using those, and we want to test other aspects. Sometimes, since I told you that water is needed to dissociate the acid, water is needed to dissociate acid, to change to the ions, to see the ions. Now, if we use like glacial acetic acid and we don't add water, instead of water we add toluenes. So with the toluenes, toluene is organic compound. It has only carbon and hydrogen. It's molecular compound. What do you expect from toluene? Toluene, is it electrolyte or non-electrolyte? With the explanation that I gave you. It's molecular compound. Doesn't have ions. So I gave you the answer already. Because it doesn't have ions as molecular compound, it's not going to be electrolyte. Okay. Toluene itself is not electrolyte. That was toluene. We add glacial acetic acid and we try to find out if it's going to be electrolyte, if it's going to be able to dissociate the glacial acetic acid. So toluene plus acetic acid. These are page 64. The table is on page 64. And the topic is effect of solvent. We want to use the solvent of toluene, try to dissociate the acetic acid. If it does dissociate, the light up would light up the light bulb. But since it doesn't, we can say that this is not dissociating. So this solvent is not dissociating. But if we add water, what's going to happen if we add water to the same mixture? So we get two layers. The top layer is toluene. The top layer is toluene. The bottom layer is going to be water plus the acetic acid. So toluene could not separate or ionize the acetic acid, dissociate, but when we add the water portion of it actually could dissociate the acid. So this is just showing the effect of solvent. The solvent should be able to dissociate the ions of your compound. So toluene not dissociating, but water was dissociating them. I'm going to place in the fume hood because toluene has very strong odor. Okay. So we studied the effect of the solvent already. Now, how do we know acid is a strong acid or is a weak acid? You can memorize it. There are 6 of the acids that they are strong acid. Everything else is a weak acid. But for today's purpose of the experiment, we are going to try acetic acid and hydrochloric acid. So we are going to add take a piece of marble and add acetic acid. We take a piece of marble and we add HCl. We are going to compare to see which one is stronger. So the acid that we are going to use in this case is going to be 6 molar acidic and 6 molar hydrochloric acid. Okay, I have to find it. Looks like we don't have it. I'm sorry. 6 molar HCl and acetic acid. Yes, one is hydrochloric, one is acidic. Okay, I don't have the 6 molar HCl here. I just requested, we will get it soon. And I'm going to see if I can do second part of the experiment. And then we do that part of the experiment. Okay. For ionic reaction, when it's a reaction, that means we have reactants, the arrow sign, and we have the product. Sometimes the reactants are electrolyte, the product is also electrolyte, so it depends on what product's forming. Sometimes the reactant is not electrolyte, the product is electrolyte. Sometimes the reactant is weak electrolyte, the product is a strong electrolyte. So it depends on the nature of the reactant and the nature of the product. So we can't say always the reactants are electrolyte or the products are electrolyte. So since we have the acetic acid now, we got the acetic acid, I'm going to actually do that part of the experiment for you. What happens if we add acetic acid to marble? And what happens if I add okay, HCl with marble. Okay, since we keep saying weak, strong, I want you to see what is happening if it's weak or strong acid. For weak acid, acetic acid, we have no bubbles, and strong acid, it generates lots of bubbles there, means that lots of activity is going on there. Okay, that's the strong acid, and this is the weak acid. Very similar experiment can be done with the zinc. So this one is the acetic acid plus marble. Okay, so we see that marble is dissolving HCl, and marble does not react, or it reacts but very slowly with the with the acetic acid. Now we're going to try the zinc also with the acetic acid and HCl. Okay. This is the HCl plus the zinc. You see the bubbles that are forming. They're very actually aggressive reaction. There is aggressive reaction. I see the vapor of the hydrogen is coming out. I usually do this experiment inside the fume hood, but for recording purpose, I took it out. And this one is the acetic acid and the zinc with not much of a activity. So this makes the difference between strong and weak acid. I'm going to transfer to fume hood so I don't get too much of the hydrogen gas in my face. And especially these are strong acids, high concentration. Leave it, put it away. Okay. So we compare the strong acid with weak acid. You saw the result for marble acetic acid, marble hydrochloric acid. Zinc, acetic acid, zinc, hydrochloric acid. So strong acid, fast reaction. Weak acid, it wasn't fast reaction. Same way, a strong acid, it's a strong electrolyte. It can, because it generates lots of ions. That's the difference. Strong acid dissociates 100%, so it generates lots of ions. If you have lots of ions, you can transfer electrons much faster. But if you have less ions, then lower number of ions, then transferring of electron is going to be slower, and the light bulb is going to be dim light. It generates very dim light. Ionic reaction. HCl, NaOH, both of them we test and they were both electric. Now we're trying to find out what happens if we mix NaOH with, with HCl. What do you think? HCl, okay, HCl, mixing HCl and NaOH. You already know both of them are strong electrolyte as separate compounds. So as separate compounds, they were strong electrolyte. When we mix it, what are the products? Products is water that is not electrolyte, but also salt, NaCl. NaCl in water is going to be a strong electrolyte. So we have products also electrolyte. So this is one of the examples that I said. Sometimes reactants are electrolyte. Products also are electrolyte. This experiment was for part 2-1. That means part 2-1 is the first ionic reaction or typical ionic reactions. A second reaction, the second reaction is reaction of ammonia with acetic acid. Acetic acid, we saw that acetic acid is non-electrolyte. I'm sorry. Acetic acid, aqueous acetic acid was weak electrolyte. Aqueous ammonia is also weak electrolyte. So let me find the aqueous ammonia. Okay. One more time, just to make sure that you have everything in one place. Acetic acid, which is a weak acid, is going to be very weak because it's giving me like very dim light, very weak electrolyte. And then we have aqueous ammonia. ammonia is also aqueous ammonia, is ammonia and water. Very dim light, even it's there, it's very hard to see it for you. What happens if we add these two as a reactant? So we are adding acetic acid to ammonia. What do we get as a result? See what's happening? As I add the acetic acid to ammonia, the product that forms is the ionic compound. The product is called ammonium acetate, made of 2 ions. And if it's made of 2 ions, it's going to be ionic compound. It's soluble because it doesn't give me precipitate. So as a result, that is a strong electrolyte because it's ionic compound and it's soluble, completely soluble. If it gives me ionic compound that is not soluble, that's a different story. That looks like that you are placing those poles inside insoluble compound like calcium carbonate or solid compound. So it's not going to, there are no ions because if it's not soluble, it's not going to generate ion. Okay, part 2-3. Part 2-3, we have sulfuric acid and barium hydroxide. Each one separately, strong acid, a strong electrolyte. Right. Okay. So I'm going to test the barium hydroxide for you. Barium hydroxide is a strong base. Barium hydroxide is a strong base. Separately, this is the reactant, barium hydroxide. And I also have sulfuric acid. Sulfuric acid is also strong electrolyte separately. The question is, what happens if you make barium hydroxide react with sulfuric acid? So we are going to try that now. I'm going to put some, which one should I add? I'm going to put some barium hydroxide and going to add slowly. I'm going to add, so I have the barium hydroxide, and slowly I'm going to add sulfuric acid. So you're with me? Okay. Going to add slowly sulfuric acid. See what's happening to the light? If I add enough sulfuric acid to react with all of the barium hydroxide, then the light is going to be dim and dimmer. It has to neutralize. So it has to neutralize. I have to add enough for it to neutralize. See, the light is getting dimmer. And at what point, one point, if I add enough of the acid to neutralize all the base, it's going to actually turn off. What does it mean? It means your reactants are electrolyte, but your product is not electrolyte. And that was one of the three conditions. One condition was your reactant is electrolyte, product also is electrolyte. The second one, which was part 2-2, your reactants are weak electrolyte, and the product is a strong electrolyte. Part 2-3, your reactants are strong electrolyte, but the product is going to be very weak electrolyte in a way that it's not actually electrolyte. It's going to turn off the light if I add enough of the two that I get to point of neutralization. So basically, there is no leftover of the acid or the base. If I have extra of the acid or extra of the base, obviously it's going to be electrolyte. But if I add enough of each to neutralize both completely, it's going to be no light and no electrolyte. Okay, another experiment, another video, it's done. I hope that you can watch it. Sometimes I tend to move fast, other times the experiment slows me down. And you probably like the faster ones better, because experiment 3, at the point that we had to get it, everything evaporated, it took long, or react, it took long. So now you appreciate fast experiments. Anyway, based on the observation that you have today, you can finish up the data sheet for experiment 5 and submit it as the assignment to assignment folder. And thank you.